So in the last lecture we have seen the definition and characterization of regular and normal spaces, and in this lecture we will continue with some properties and some examples of regular and normal spaces. So let us start with a theorem which gives regularity for subspaces and for product spaces. So here's the theorem. The first part says that a subspace of a regular space is a regular space on its subspace topology, and the second part says that the arbitrary product of regular spaces is regular in the product topology. So let us see a proof of this theorem, but just I want to give you as an exercise prove these statements for when regularity is replaced with the Hausdorff property. So for Hausdorff property instead of regularity property, so I leave this as an exercise to you. So let us look at the proof for the first part. So let X be a regular space and Y be a subspace. So we have to show that Y is regular. So note that as a subspace of a Hausdorff space, since X is supposed to be regular, it is already Hausdorff. So as a subspace of a Hausdorff space, Y is Hausdorff. This is from the exercise above that I gave. And so we just have to show the separation property for a point and a closed set. So let X be a point in Y and B be a closed set in Y, such that X does not belong to B. And now we have to produce open disjoint sets containing X and B in the subspace topology of Y. So we will of course use the regularity of X here. So note that B is equal to B closure in the subspace topology of Y, but this is, as we have seen before, equal to the closure in X intersection with Y. And since X belongs to Y and X does not belong to B, this implies that X does not belong to B closure in X. So the closure is in X, and now we can use the regularity property of X. So from the regularity property of X, we have that there exists open sets U, V in X, such that X contains U contains X, B closure is contained in V, and U intersection V is empty. So we have found disjoint open sets containing X and B closure respectively, and then the sets U intersection Y and V intersection Y are open sets. We have that X belongs to U intersection Y, so open sets in Y, of course, in the subspace topology, and X belongs to U intersection Y because X belongs to both U and Y, and B closure intersection Y, which is just B it is a subspace of V intersection Y. So now we have found disjoint open sets. So of course U intersection Y intersection V intersection Y is gonna be empty because U intersection V is empty. So so we have disjoint open sets in the subspace topology of Y containing X and B respectively, and so we are done. So this implies that Y is regular. Now similarly, to show that if X is a product, say an arbitrary product of X alphas, X alpha regular for each alpha in J. So we have the product topology on X. So with the product topology, and we have to show that X is regular. So in this case, again we have the arbitrary Cartesian product of Hausdorff spaces is Hausdorff. So X is Hausdorff, again from the exercise given above. And we just have to show the usual regularity property, right? So now to show this, we will use the previous characterization. Use the characterization from the previous lecture. In the previous lecture, and remember that we had an point X and an open neighborhood, and we have to find a smaller neighborhood whose closure lies in the given open neighborhood. So for this, let X belong to this set X, and U, which I write as the product of U alphas, be a neighborhood of this point X. Now we have to show that there exists a neighborhood V of X such that X belongs to V is a subset of V closure, which is a subset of U. So this was the equivalent characterization of regular spaces. So to show this, we will find V in terms of the U alphas. So for each alpha, we find a V alpha, and then we take the product. So for each alpha, we use the regularity of X alpha. Using regularity of X alpha, we choose a neighborhood V alpha of X alpha, which is nothing but pi alpha of X, and this is a point in X alpha. So for each alpha, such that X alpha belongs to V alpha, which is a subset of V alpha closure, and this is a subset of U alpha. So we have to be careful here, because we don't want V alpha to be a proper subset of X alpha for infinitely many alpha, or rather except finitely many alpha. So if U alpha is equal to X alpha, then V alpha is chosen to be X alpha as well. So this gets rid of this problem, because we only have finitely many proper subsets U alpha in the product topology. So for the rest of them, we just take V alpha to be X alpha. And so now we claim that let this V be a product of all these V alphas, and this is our required neighborhood of x that works. So then we claim that x is in V. It's a subset of V closure, and this is a subset of U. So the only thing needed to prove here is that V closure is a subset of U, and this is because V closure, so note that V closure is the product of V alpha closure. Okay, so I leave this as an exercise for you to check that when you take the closure in the product topology, then you get the product of the closures. Okay, and so V alpha is equal to the closures, the product of the closures, and this is of course a subset of the product of U alphas, which is U. And so we are done. So we have shown that X, which is the product of X alphas, is irregular. Now let us come to discuss some properties of normal spaces. Unfortunately, so let me put this as a remark straight away. The analog of theorem 2.1 does not hold for normal spaces, and so to just to see what that means is that subspaces of normal spaces may not be normal, and Cartesian products of normal spaces may not be normal. So the analog of theorem 2.1, which was given for regular spaces, does not hold in general for normal spaces. So even though normal spaces aren't so well behaved, there are two classes of topological spaces which are normal, and they give already a large class of examples of normal spaces. So what are those two classes? So let me put this as a theorem. So first is that every metrizable space is normal, and every compact Hausdorff space is also normal. So we have already seen that metric spaces and compact Hausdorff spaces are regular. So by the separation lemma, so just as a note, by the separation lemma in week 9 lectures, both metrizable and compact Hausdorff spaces are regular, because there we prove that a point and a closed set can be separated by disjoint open sets. So now this is a stronger result, and it says that both these examples also give you normal spaces. So let us look at a proof of the first part, and I will leave the second part as an exercise because this is sort of easier, and in fact both these proofs are on the same lines for the proof of the separation lemma where we prove that these two examples give regular spaces. So I'll prove only the first part, and I will leave the second part as an exercise. So let's look at the proof of the first part. So to prove the first part, recall that a metrizable space X is regular, and we will use this property to prove normality. So let A and B be closed subsets, closed disjoint subsets of X, and we have to show. So the normality property requires us to separate closed sets, disjoint closed sets. So we have to show that there exists open sets U containing A and V containing B, such that U intersection V is empty. So we create U and V using the regularity property. So for each A in A, choose epsilon A, radius epsilon A, such that the ball with center A and radius epsilon A does not intersect B. Okay, this is possible because B is closed set and A does not belong. A and B are disjoint, so this small a does not belong to this capital B, and therefore we have a radius such that the metric ball centered at A with radius epsilon A does not intersect the closed set B. Similarly, for each B in B, choose epsilon B such that B epsilon B. So here maybe I should take epsilon A by 2 and epsilon B by 2, as you will see. So the metric ball with radius epsilon B by 2 centered at B does not intersect A. And now we can define the open sets U. So let U be the open set BA with radius epsilon A by 2 now, and the union is taken over all A in A. And similarly, the set V can be defined using the union of the metric balls BB epsilon B by 2. And I claim that first of all, it is clear that A is a subset of U, B is a subset of V. So the only thing, and of course U and V are open, and so the only thing to show is that U intersection V is empty. So let's prove this. So to show that U intersection V is empty, so suppose that we have a point in U intersection V, and then we will arrive at a contradiction. So this means that Z belongs to B A naught epsilon A naught by 2 for some A naught in A, and similarly Z belongs to B B naught epsilon B naught by 2 for some B naught in B. And so this means that Z belongs to the intersection of these two sets, intersection B naught epsilon B naught by 2. And so now take the distance between A naught and B naught, and this will give us the contradiction. So the distance between A naught and B naught by the triangle inequality can be estimated using plugging in the point z, and the first part is less than epsilon a naught by 2, and the second part is less than epsilon b naught by 2. So this is epsilon a naught plus epsilon b naught by 2. Now if epsilon a naught is less than or equal to epsilon b naught, then this implies that the distance between a naught and b naught, which is, as we have shown, is less than epsilon a naught plus epsilon b naught by 2. But if epsilon a naught is less than or equal to epsilon b naught, then this is less than or equal to epsilon b naught plus epsilon b naught by 2, which is nothing but epsilon b naught. And this means that a naught belongs to the metric ball with center b naught and a radius epsilon b naught. And this is a contradiction, because we chose for each b, we chose the epsilon b's such that it does not intersect a. So this is a contradiction. Similarly, if we assume epsilon b naught is less than equal to epsilon a naught, this gives a contradiction just by switching the roles of a and b, and therefore this implies that u intersection v is empty. And so we have shown that x is regular. So this gives us a large class of examples already. So of course you have that R is regular, is normal. Then any subspace of R or even Rn is normal, because subspaces of metric spaces are also metric spaces. And we can have other examples as well, but in general, so this is another remark. In general, it is a very difficult property to prove that a given space is normal. And just to illustrate this, this is an open question even now in topology. So we do not know if the product space R omega with the box topology is normal. So this is still an open problem in point set topology. So some results are known, but in general it is not known whether R omega with the box topology is normal. So to give some more examples, or rather let me give a non-example of a space, so a space that is not normal. So non-example. So if J is infinite, then the countable product Rj, which is just the product of uncountably, so this is uncountably infinite, is uncountable, then Rj is not normal. This is known, and the proof is rather long, and I won't give it here, but let me just give the reference from Munkres, which so this proof is given as an exercise, and I encourage you to go through that exercise and prove all the steps. So let me give the reference for that exercise. So this is exercise 9 in section 32 in Munkres in my edition. Please note that the exercise number might change with the edition, but you will be able to find it, no doubt. So now this is an illustrative example because this shows three things. So this non-example shows that first that of course this is in the product topology, right? So in the product topology, so this shows that a product, so first of all, a regular space need not be normal. We have shown that Rj is regular since R is regular from and we use theorem 2.1, which showed that arbitrary Cartesian product of regular spaces is regular. So this is an example of a regular space that is not normal. Secondly, this space Rj is homeomorphic to the subspace 0, 1 to the j. This is nothing but the product of the intervals 0, 1 in 0, 1 closed to the power j. So this is the open interval and this is the closed interval. Now when you take the closed interval and you take the arbitrary Cartesian product, this gives you a compact Hausdorff space by Tikhonov's theorem, which is a compact Hausdorff space by Tikhonov's theorem, and therefore is normal. Okay, so it is normal. However, this subspace, the Cartesian product of open intervals 0, 1 is not normal. So it shows that a subspace of a normal space may not be normal. Subspace of a normal space may not be normal. And thirdly, it also shows that an uncountable product of normal spaces need not be normal. So the analogues of theorem 2.1, first that subspace of a regular space is regular, and the arbitrary Cartesian product in the product topology of regular spaces is regular, and neither statement holds for normal, for the normality property. So before before we end the lecture, I just want to give a statement of a theorem which gives a nice criteria when a regular space must be normal. So this is a theorem. So I'm not going to give the proof, and I refer you to the Munkres's book for the proof. And the statement of the theorem says that a regular space X with a countable basis is normal. So if you have a space which is already regular and it has in addition basis which is countable, so it means that it only has countably many sets in the collection, in the basis collection, so then the space is automatically normal. And just to give you a reference, this is theorem 32.1 in Munkres's book. So again, in my edition, and you might find the numbers different, but it's there in Moncrief's book. So I encourage you to go through the proof. It's a very nice idea, and it shows that under some additional conditions, a regular space becomes normal.